Hello, everyone. Welcome to this edition of the BRAG. It is a great pleasure for me to introduce our speaker today, Hamid Hassanzadeh from UFRJ. He will tell us a genus explanation of Buchsbaum-Rim multiplicity. Please, Hamid.
Okay. Thank you, Carolina, and thank you for the invitation, all of the BRAG organizers. This is my joint work with essentially my students, Viníçius Bouça, Thiago, Fiel, and José, Naeliton. And we are going to talk about the Buchsbaum-Rim multiplicity, and we believe that we found a new homological interpretation of this important multiplicity number. I'm trying to be less technical, as this topic is very technical. I saw that Steve Kleiman is here, and I learned many things from his papers. And in one of his papers, he said that the real is in the detail. You know, the paper was so delicate, and really this sentence makes sense to me, that really there are so many details there that that one really feels that. So I don't want to bother you to just go to detail, but instead of this, I will go through the main ideas and the inspiration of this work. Okay, so the multiplicity theory is one of the oldest and maybe the most important classical invariant in commutative algebra and algebraic geometry. So the first definition of multiplicity comes after Hilbert's work. So just let me go through the basic definitions. So let's assume R is an Noetherian ring over an Artinian base ring. And then Hilbert defined the Hilbert function of R to be the length function of the nth component of this ring over R0. And then he shows that eventually for big enough n, this function is a polynomial function of degree dimension of R minus 1, I denote by d minus 1, and the leading coefficient is just e d minus 1 factorial into the d minus 1, etc. And this e is called the Hilbert multiplicity of the ring R, and it has a very critical role to understand the singularity of the varieties, especially the isolated singularities. So to say better about isolated singularities, so Samuel generalized this idea of Hilbert for local rings. So this was needed because one has to go through the isolated singularities. So one needs to localize things. So then for a local ring, Samuel defined, so we say that an ideal is a parameter, is a ideal definition if the radical is m, and then Samuel defined the Samuel function, okay, to be the length of this final length module. And he also showed that this is, oh sorry, then just a second. Can you see the WhatsApp message here or no? Is it okay? I mean,
we see well, yes.
No, okay. No, but do you see the other? I mean, except the board. Do you see other message on my?
No. We only see the board.
Okay, good. Okay, so then he defined this length function and showed that again this is a polynomial ring of dimension d. This is the dimension of R, and the coefficient, leader coefficient, this, etc. So we have now the local definition, and as I said, this has a very critical role to understand the singularities, and of course used by Hironaka in 1964 to settle the resolution of singularity in characteristic 0. But so this state is critical in this theory that I'm going to talk, because so it was at this year that Zariski, so when he understood that the resolution of singularity now is out, then he paid more attention to classify the singularities. So instead of just resolving singularity, he asked when one can decide one singularity is similar to another one. Okay, so like, you know, this is the typical picture. So you have a family of singular curve, but you can understand if their singularity are essentially the same thing. Okay, so then Zariski wanted to understand some kind of equivalence between singularity, and he looked to define the equisingularity, so equivalence between singularity. And finally, he defined equisingularity between singularities. So even the concept was not easy at the beginning to settle. So Whitney also, from topological point of view, he tried to also define the equisingularity. So literature is interesting at this one because Zariski was not, you know, didn't like the Whitney's definition, and so there are many discussions at this point. So one of the main feature in this theory is Gaffney, who developed quite a bit the theory of equisingularities. So Gaffney had a very deep study. I mean, well, not only Gaffney, I mean, Tessier, so there are many, Steve Kleiman, so many people had contribution to this theory. So, but Gaffney has a significant contribution in my opinion, but then, okay, so he had a very deep understanding of the singularity of the theories of that Riesz and other algebraists established for this theory. And especially he understood that to understand equisingularity, one needs a theory of integral closure of modules. So this is what led him to understand this theory that was developed in 1960s by Riesz and others. And beside that, he also needs some invariant that could measure the singularity in family. Okay, so how to measure singularities in family? So he had a very nice, how to say, investigation in many algebraic, you know, territories, travel, talk to the people. So Kleiman has a nice review of what happened in Gaffney in his, you know, discovery of this theory. So then, so he figured out that finally to have a theory that could explain the equisingularity theory, he needs a generalization of this Hilbert multiplicity for modules. Okay, so multiplicity of modules. And through some talks with Riesz and others, he figured out that at the same year, in 1964, Buchsbaum and Rim had already developed this theory. So Buchsbaum and Rim in this year, so developed the theory of multiplicity of modules, which we call them nowadays the Buchsbaum-Rim multiplicity. Okay. So just, I think it won't be bad if I just recall the definition of Buchsbaum-Rim multiplicity, right? So the idea is the following. So you have a module M. So generated in G elements and related in F elements. So this module is presented by a matrix, by a G by F matrix. Right? Then you look at the symmetric algebra of M. So for that, you need to look at, you choose new variables, T1, Tg. And then you just multiply this matrix into this matrix. And then you have linear forms in T. So you have F linear forms in the variables T. These are the ideal of definition of the symmetric algebra of M, right? And then I think, yeah, that's it. Then the idea is to understand the Riesz algebra of module. So the Riesz algebra of module. So this is very first definition by Riesz. So you know Riesz algebra of an ideal is the sub-algebra of the polynomial extension generated by the generator of the ideal, right? So the Riesz algebra of module is the sub-algebra of the polynomial ring generated by these forms. Okay. So in the case that we have only one line, then this is the ordinary definition of the Riesz algebra of an ideal. But when you have a matrix, then you have, t variables, and then you have a more complicated algebra. But then this is the Riesz algebra of this module. And then Buchsbaum-Rim shows that if the length of M is finite, then this function, so we call this matrix by phi. So p phi of V, which is the length function of S, this algebra over this subalgebra in degree V. Okay, so they show that this function is eventually a polynomial ring. And with coefficients, so for V big enough, this is a polynomial ring with leading coefficient a multiplicity d plus g minus 1 factorial v to the d plus g minus 1. So in the case that g is 1, so it means that you are working with a cyclic module, which is indeed an ideal. So in the case that g is 1, this theory covers the usual, Hilbert function, the usual theory of Hilbert multiplicity. But in the higher generating modules, then this is a much more general theory. But as you can see, not everything is, not as straightforward as the Hilbert theory of multiplicity, because we have more thing here to study, and there are many details. Anyway, okay, so let's now talk about another interesting thing, which is intersection theory. So, in the modern intersection theory is based on two main theorems. One is the Chow moving lemma, and the other is the Serre correct definition. So I said correct because Serre said correct, because it is not the definition of Grobner and so on. So this is the correct definition of the local intersection multiplicity. Okay, so this is what Serre defined, and these two together indeed complete the axiom established by Weil to understand the intersection of varieties or schemes. So this definition I want to concentrate now. So this definition is the following. So Serre in 58, in his course in Collège de France, so he established this. So let X be a regular scheme, Y and Z, two closed subscheme of X, intersect properly. Let W be an irreducible component of the intersection. Then Serre defined the intersection multiplicity of Y and Z aligned W to be the sum of -1 to the I, the length of A of Tor I of A over A and A over B, I from 0 to infinite, whatever, it is a finite sum at the end. And this A is just the stock at the generate point of W And A and B are ideals of definition of Y and Z. Okay, so you see, very non-trivial definition, right? Very non-intuitive definition, as the Grosvenor definition was only the zeros toward, so A over A tensor A over B, but as Serre said, this was the right, and this is the correct definition of intersection multiplicity. But then there are many things to prove. If you want to show that this is the true definition, then you have to say that, okay, this definition satisfies all of the axioms that Weil wanted. And then this is what Jean-Pierre Serre did in his course in Collège de France, and it is in his book, Local Algebra. Okay, at the end, so one of the very first and important property of this number is that this is a positive number. Okay, this is a positive integer. So to show this, Serre used a technique which is called reduction to diagonal. So it has many steps to get to this answer. So reduction to diagonal. And to reduce to diagonal, so but honestly, Serre generalized this to modules M and M. So instead of cyclic module A over A and A over B, he just studied Tor for two modules whose tensor product has finite length. But well, this is what we need here. So reduction to diagonal. So by reduction to diagonal, he had to study the complete tensor product. So after doing that, so you see every step is a bigger step. Okay, so after doing that, he reduced to the case that A is a complete intersection. Is a regular sequence. Okay, complete intersection. So when you get to complete intersection, then Tor is not just the abstract module. It is a more concrete thing to compute because we know the resolution of a complete intersection. We know the free resolution, the minimal free resolution of a complete intersection, and it is the Kuzu complex. Right? So the magic word appeared here, which is the Kuzu complex. So when you have a complete intersection, so let's say A1, AF, the complete intersection over ring A, then the Kuzu complex of this sequence and A is just the DG algebra structure of the free module AF. So it's just the exterior algebra of AF. And if you want, it is just the complex A, and you have A to the F, and then you have A to F choose 2, and then at the end you have A, F choose F, and then the maps here are just the natural map. So you send E1, EI to the sum of -1 to the J, and then you set J, and then E1, EJ out, and then EI. So this is just the map that appear everywhere in algebraic topology, in simplicial complex, and here is in Kuzu complex. In 2018 in Campinas, I was in the School of Algebra, and I talked more about the history behind this Kuzu complex, right? But anyway, this is the Kuzu complex, and this is nice because we know exactly what the maps are, what the modules are, and when this is a complete intersection, then this is the free resolution of I over A, and then when you want to calculate the Tor, you just need to tensor A to the A over B with the Kuzu complex and just calculate the homologies. So these are just the homology module of the Kuzu complex, right? So then to prove the positivity, so in this case, the positivity is just the sum of -1 to the I of the lengths of the Kuzu homologies of A over AB. Okay, now we get to another beautiful formula of Serre, and he showed that this alternative sum of Kuzu homologies, which is a reminiscence of the alternative sum of Bethe numbers in the simplicial complex that define the Euler characteristic of the variety. So here he proved, maybe inspired by that idea, he proved that this is just the Samuel multiplicity of this parameter ideal for this ring A over B. And the multiplicity is a positive number, right? So this was the way that Serre proved the positivity of the intersectional multiplicity. And this is the formula that I want to focus on. And I want to state a similar formula for the Buchsbaum-Rim multiplicity in terms of the Koszul homologies, right? And I will say why the title is genus just at the end when I complete the proof. Okay, okay. So now I want to go to this. So let me stop for 1 second and to see if there is any question. Anything interesting or not interesting here? Okay, so let me continue. So people, as I said, Buchsbaum-Rim had this idea to generalize the Hilbert function and finally the Hilbert multiplicity or Hilbert-Samuel multiplicity. So they were aware of this formula of Serre, and they knew that Serre established this alternative sum of homology as the, this is an homological interpretation of a multiplicity, right? So they also wanted to do the same thing for the Buchsbaum-Rim multiplicity, but the point that it was not possible to have an ordinary Kuzu complex. By ordinary Kuzu complex, I mean whatever everyone knows from very basic course in commutative algebra, right? So it was not possible at the time to explain this at the homologies of Kuzu complex. So instead, they generalized the idea of Kuzu complex to another more sophisticated complex that they called the generalized Kuzu complex, and they could finally establish a formula of the Buchsbaum-Rim multiplicity in terms of the homology of that generalized Kuzu complex, right? So to say, so the Kuzu complex generalized, so maybe historically first Egon and Norskott, they generalized the idea of Kuzu complex that was a complex of Kuzu for one sequence to a complex of module of Kuzu for a matrix, right? So Egon and Norskott asked, okay, so the Kuzu complex is a complex created for a matrix with volume line. We want to construct a Kuzu complex for a matrix of G lines. So how they did, they just tried to construct a Kuzu complex for each line, and in a clever way, they just glue all of this Kuzu complex and create a bigger complex. So the benefits of this Egon-Norskott complex is that they provide a solution for the determinantal ideals, right? Okay, so what Buchsbaum-Rim thought was the following. They said that, okay, you have a matrix, C11, C1G, C1F, CG1, CGF. So this matrix, it seems to be the beginning of a resolution of the module M, which is the co-kernel. So how can one naturally extend this resolution to the left? So you remember that the Kuzu complex was just one line. Okay, and in natural way, you move to the left by considering the exterior powers, right? So they wanted to repeat the same idea for any module and for any matrix. So it was the way that they construct a complex, which is called the Buchsbaum-Rim complex nowadays. And they indeed show that this Buchsbaum-Rim complex, if the module has finite length, then the formula for Serre. So if you replace the Hilbert-Samuel multiplicity with Buchsbaum-Rim multiplicity, and you replace the Kuzu complex with Buchsbaum-Rim complex, then you have a similar formula for the Buchsbaum-Rim complex, but it was not the Kuzu complex, it was the Buchsbaum-Rim complex, right? So the point was that these two ideas of Egan-Norskott and Buchsbaum-Rim was unified by Buchsbaum and Eisenbach, and independently by Kirby in 80s. So they introduced a family of complexes. So for any maybe V, so there are many names for this complex. So like V, or like K, V, V. So these are for any index V. So they created a new family of complexes that are generalization of the Kuzu complex, and the zero element of this family is the Egan-Norskott complex. The first element is the Buchsbaum-Rim complex, and so on. Okay, so this is a generalization of this idea of generalizing the Kuzu complex by Buchsbaum and Eisenbach, and they created a family of complexes. So the nice about this family is that Kirby proved that when the length of M is finite, then the sum of -1 to the I of the length of the homology of this family of complexes is independent of V. Okay, so in some sense, these complexes are the same or have the same characteristic. So this number is called the characteristic of the complex. Okay, so all of this family of complexes have the same characteristic. Okay, this was about the history. So let's go to our main theorem. So what we did, we looked for some ordinary complex instead of going to generalization of Kuzu complex, and some we just want to explain the Buchsbaum-Rim complex as an ordinary Kuzu complex. So let me recall you again. So we have this matrix. So 1F, G1, GF, G or F. So quite general things like Noetherian is enough for us. Then you consider these new variables T1, Tg, and you time this into this matrix F. And you have this ideal of definition of the symmetric algebra. And the Kuzu complex that we want to indeed work with is just this complex. So you have the polynomial extension R by the variables T1 and Tg. And then we just look at the Kuzu complex K of gamma 1, gamma F, which are linear forms in TIs, right? With coefficient in S. So this is the Kuzu complex that we want to work. So as natural as one can believe, right? And so the main theorem is the following. So the theorem so let R and M be a Noetherian local ring. M finitely generated and finite length module with the matrix presentation phi here. Let Hi be the ith homology of Koszul of gamma 1, gamma S or S. And consider the Hilbert polynomial of Hi, okay, the Hilbert polynomial at V, okay, that's it. So this ring S is a standard ring with degree 0 here, and all of these guys are in degree 1. Okay, so like this, we define the Hilbert polynomial. Then we prove that for any V, the sum of -1 to the I of these polynomials is the Buchsbaum-Rim multiplicity. I just have to add one detail here, that we assume this phi to be a parameter matrix. Otherwise, this sum is 0. So it is a parameter matrix. And by that, I mean F is D plus G minus 1. But this is not a big deal. Every thing you can find at the end, the parameter matrix for any module. But anyway, so if not a parameter of matrix, then this sum is 0. Otherwise, the sum of these polynomials is the Buchsbaum-Rim multiplicity. So what's nice about this theorem is that, so in contrast with the Serre formula, that was a formula of the constant. So you see here, these are just numbers, and the sum, alternative sum of this number is the multiplicity, right? But here we have polynomials. But still, the alternative sum of this polynomial is the Buchsbaum-Rim multiplicity, right? So during this, we did not use the proof of none of the technique of Serre. But so in our case, when you, for example, when you put G equal to 1, then you recover the Serre formula, right? So when you set G equal to 1, then one recovers Serre's formula. But even more beautiful is when you put V equal to 0, then you have your constant integer of the Hilbert polynomial of each homology, right? So then you have the constant terms. So let me abuse the notation and call this the arithmetic genus by some arithmetic genus. Okay, so then if I want to rewrite the Serre formula, which is this one, for Buchsbaum-Rim multiplicity, so the formula would be like this: the -1 to the a of the arithmetic genus of the, maybe I will better to, well, let me be right for this. It's not killing us, but then I will correct this wrong notation, right? The Buchsbaum-Rim multiplicity. Okay, so I would say this is the arithmetic genus explanation of the Buchsbaum-Rim multiplicity. So you have your module M, you look at the ideal, you look at the equation of the symmetric algebra and look at the Kuzu of that complex and look at the homology of the complex defined by equations of the symmetric algebra. The alternative sum of the arithmetic genus define the Buchsbaum-Rim. So in the case that G is 1, this arithmetic genus is indeed the length of the module. And this formula recovers this formula, right? So just okay, I need like at most maybe 5 or 10 minutes to talk about the sketch of the proof and then answer the question. I don't know how much time do I have, Caroline?
You have time still.
Good.
Yes.
Maybe I talk too fast. I don't know.
No, it's good. Yes, take your time.
Okay. So if you are not bored, so I can go through more details, talk about some of the detail, how we prove the main theorem. Okay, as it seems, but it is not very easy to prove this theorem. You know, we had very non-trivial techniques to arrive to this conclusion. So one of them, so then a sketch of proof. One of them was that we need a better understanding of the Eisenbach-Buchsbaum family of complexes, or a better understanding of the Buchsbaum-Rim complex or Egan-Norskott complex. So what we discovered first was that all of the Eisenbach-Buchsbaum-Eisenbach complex, Eisenbach family, all of the members of the Buchsbaum-Eisenbach family, CD, so, or equivalently, the Kirby family, all of this family of generalization, they are just the strands of a Koszul check spectral sequence. Okay, so this was a work I did with Viníçius in 2019. Okay, so to do that, so with Viníçius, so we study, so again, let me recall the notation. So we had this matrix here, yeah, and we created these linear forms, which are the ideal of definition of symmetric algebra. So we take this Kuzu complex of these guys, and you tensor this with the check over the variables t, and you look at the horizontal and vertical spectral sequence coming from this double complex. So the nice thing is that so when you write this horizontal and vertical, so the vertical collapses at the line is the last line, and the horizontal spectra provide connection between the last line in the vertical spectra and the first line of the double complex. And this connection is provided by the transgression mapping the spectral sequence. And we figure out that for any degree, so if you look at this bicomplex in any degree V, so you have, and you do this procedure here, you have a new complex, right? And all of this new complex, any of this new complex is a member of the family of Buchsbaum-Rim complex. So it was very nice because the description that Buchsbaum-Eisenbach or Buchsbaum-Rim, or so it was not universal, it was not that functorial. So when we figure out that, it was like a release for us because it opened many doors to us, and we could systematically understand better the structure of these families, just looking at the Kuzu and the local cohomology modules, right? So the first step was this one. The next step was that, okay, when you look at the homology of the Kuzu complex here, okay, so these are not finite length things. These are not finite length module, even if the module M is a finite length. These Kuzu homologies are not finite length because you have new variables here. Okay, but what we discovered was quite amazing, that when you look at the shiftification of these guys, so instead of this module, you go to the shifts, and then you look at the homologies, which are the local cohomologies, right? I mean okay, let X be the proj of S. So then when you look at the homologies, so we prove that these are of finite length for any Q, P, and V. So I mean Q from 0 to whatever, P from 0 to F, and V whatever V, right? So although these guys are not finite length, but these cohomology modules are finite length. So then you can define this alternative sum of the finite length module. And then although R here is a ring, R is not a field, R is not Artinian. Remember that our ring S, here we have proj of R. This is P G minus 1 over spec R, right? So the base scheme here is not a field, not a notorious. So it's not non-trivial scheme here, right? So this is not exactly the same theory that we studied from the beginning of Hilbert theory. So here the base ring is a Noetherian local ring, and we only need that. So anyway, even though if the ring, if the module M has finite length, and you look at these Kuzu homologies, so all of these local cohomology modules are of finite length. So at the end, you can define this alternative sum function Q length of HQ X HPV, and then like what we do in the case of Hilbert polynomial explanation in terms of the local cohomology here also works, and we can show that this is a polynomial ring with positive coefficient. Okay, so this polynomial ring is what we denote by HP of V, but indeed HP of V, I mean, there are some technical thing here that you have to substitute HP, I mean the module HP by the saturation of its HP. Okay, so this module now has elements of finite length, has component of finite length, and then you can consider the Hilbert polynomial of this module in degree V. I don't want to go to the details here, but anyway, by some ignorance, we can just talk about the Hilbert polynomial of this module as the Hilbert polynomial of the piece Kuzu homology of that sequence, right? So then you found that this module is the Hilbert polynomial, and what at the end what we did, we showed that the our Koszul check spectral in degree V, when you totalize and then you calculate the characteristic of them, then you have alternative sum of these Kuzu homologies for any degree V. And then we use the theorem of Kirby that proved that this is independent of V. And finally, we proved that the Buchsbaum-Rim multiplicity is this number for any V, right? So finally, to have the correct definition, I said that so in degree 0, PHV in degree 0 is just the length of this complex, this cohomology with zero shift, with no shift here. And this is what we call the characteristic of a shift, right? So indeed, if I want to explain better, this, I mean, correctly, this is the length, this is -1 to the of characteristic of these shifts. Okay, I think I will stop here.
Thank you, Hamid. Are there questions for Hamid?
I have a quick remark. At the very beginning, you mentioned the moving lemma as a main tool in order to define multiplicities, intersection multiplicities, and so on. But then in the 70s, early 70s, Fulton and McPherson devised a way to build intersection multiplicity, the intersection index of intersection index using the reduction to the diagonal as in Serre, but going up to the projectivization of some normal bundle that appeared, and then using some general tools, he could get intersection multiplicity as a classical multiplicity using not downstairs but upstairs in this bundle, right? I wonder if any of this has an impact in the Buchsbaum-Rim theory.
Yeah, you know, Professor, this is our ambitious to arrive to that. Indeed, this would be very preliminary, you know, things. This is what we look for. I mean, my own idea is that we continue in this way and we try to understand better if we can generalize the theory of, I mean, the Serre's idea that used in the multiplicity of Hilbert from Buchsbaum-Rim multiplicity. But maybe we may have some application in the equisingularity theory. But indeed, at the moment, I have no idea how to go further. This is just the very basic, you know, equality that one may need. But the next step, yeah, I appreciate the question, very nice. But indeed, I thought about that, but I have no idea how to answer that.
And thanks for your beautiful talk. I mean, it was really impressive.
Are there more questions for Hamid? I have a very naive, question. Whether if this can be somehow has some geometric realization within foliations, do you think that that this may have some geometric manifestation there? Because some years ago, in a work with Mauricio, we used the Ego-Northcott resolution to study foliations that were by looking at the certain foliations.
Oh, I see.
In connection with their singular loci. So I don't know, I was wondering whether this can be...
You know, I believe that we have a very nice understanding of Ego-Northcott complex. I believe that I understand Ego-Northcott by heart. So I will be very happy to read that paper.
Okay, maybe we can discuss it
yeah, of course. Yeah.
sometime soon.
Yeah.
Wonderful. Okay, so are there any more questions for Hamid?
Okay. Can you hear me?
So
Of course I can hear.
I can hear you, yes.
Great. What you've written there, you have an alternating sum of lengths equal to a polynomial ring. What does that mean?
You mean if this polynomial makes sense, you mean?
How is an alternating sum of numbers a ring?
Well, some of the polynomials, like some of the polynomials. I mean, when you sum up these polynomials here, you just, so it says that all of these polynomials, so the biggest term in the polynomial eliminates one by another, and the only thing that remains is the constant term. Right?
But that's a number, no? Well, you have polynomials there, but on the other...
Right, you have polynomials, but then sum up the number, they disappear.
Yeah, so that gives you a number, the Buchsbaum-Rim multiplicity.
The constant, you have constant, so this is what I call the arithmetic unit at the end, because this is just the arithmetic unit that makes sense, contribution to construct the Buchsbaum-Rim multiplicity. The constant term of those polynomials sounds like the Buchsbaum-Rim multiplicity. I can show an example if you want.
Yeah, well, no, leave that page there for a minute, if you would. All right, let's look at the example.
You know, there are some noise in your microphone, but...
Oh, sorry.
Can somebody help me? So let me just it's nice to show you an example.
Sure.
Yeah, so let me show you an example that you already wrote in the paper.
Okay.
I found the example. Okay. So for example, if you look R to the 2, 1, and you take the matrix to be 0, 0, 4, okay. And you take n, the filter of this matrix, right? This is the parameter matrix. This is the parameter matrix for n because 3 equals to the dimension 2 plus minus 2 minus 1. So this is the parameter matrix here. And it is shown by Ubi and also by some others that the Buchsbaum-Rim multiplicity of 1 is just 9, right? So what we do we look at the coefficients here, so we have the quantity given this. So this is our 101 geometry. Almost something to check. And we have only two pieces of homologies, one algebra, and this is the canonical module of the geometric algebra. And then one can use some technical things, and then to show that they use the polynomial of x0 over its saturation. In this slide, so there is no contribution of this function that
Okay, but now if we could go back to the last page. You see the sum in the middle? It's in the middle of the page. Go, there we go, that. Now, right after the box, you have an equal sign. An equal sign. Equals polynomial ring. Do you really mean that the sum is a polynomial ring? Okay, that's better. Okay, that makes sense now. Okay. Another question is the term arithmetic genus. Does
I add these limitations. I confess that I add these limitations. I barely wanted to say the constant terms in the polynomial, in the Hilbert polynomial.
So is it just a formal connection, or is there some connection to the arithmetic genus in geometry?
Sure. You know, what I would say more correctly is the Euler characteristic of the simplification of this sheet.
Mm-hmm.
And I call, I would say that because this is the sum of these terms, then this is equal to 0, then I call this the arithmetic. This is the Euler characteristic of this.
Where does the term arithmetic genus come in?
Well, the arithmetic genus, there are some small differences here. You know, for variety H, the arithmetic genus is -1 to the dimension plus 0 minus 1, right? Then this is the Hilbert polynomial. Right? So here we take out this -1, so up to then you have individual arithmetic. So one can formulate this by adding the -1 here and then have the right to move up to the arithmetic.
I see. So it's a formal analogy.
I add this limitation. I use instead of this -1.
Okay. One more question. Have you studied the behavior in a family? Suppose we have a flat family of modules. What can you say about the Buchsbaum-Rim, or about your work? Is there any semi-continuity of it, or anything of that nature?
No, I know what you mean. I read that paper of you. So my idea is, to create in that case, so my idea is that we can consider, we can consider family of the Kuzu complexes, right? Of the Kuzu complexes generated by the equation of the geometric algebra, right? And then the study with the totalization of that and each is the family. Each is the Buchsbaum-Rim of any member of the family, and the totalization of the double complex, which we have a new invariant that I think nice question, and I'm going to work on that. I mean, my next project is in this.
Okay. Right. Bob, get any information about integral closures from this? Information when the Buchsbaum-Rim multiplicity vanishes, then we have a finite extension somewhere. Do you have any results in that direction? Well, okay, apparently not. Yeah, if it doesn't ring a bell, then that's fine. Okay, thank you very much.
Are there more questions for Hamid? Well, if not, then let's thank Hamid for this beautiful talk again.